All right, Tyrone, go ahead.
If a point is on the bisector of an angle, then it is equidistant from the sides of an angle.
Okay. So if a point is on the bisector, so take a look at what we have in this scenario. I have an angle. What's the bisector of that angle? Which ray is the bisector?
Wait, can you repeat the question?
Sure. I have an angle, so I'm looking over here at this diagram. I have an angle that's being bisected. Which ray is the bisector?
E?
So that remember, we have a ray, not just C. You guys are right, but remember, since it's a ray,
Is it PC?
PC, yeah. So this one's the bisector. And what it's saying is that if a point is on the bisector of an angle, then it is equidistant from the sides of the angle. So the point that is located on the bisector is point C. And what it's telling us is that point C is equidistant from the sides of this angle. And when you have an equidistant, when you connect point C with line segment PB and line segment PA, when you connect it, what kind of angle does it create?
When you connect, wait, what?
All right, when I connect point C with PA and PB, what type of angle is created? Look at the diagram. What kind of angle is created when I connect point C with the A and with the B? This is not a hard question. P to A, I mean C to A, C to B, what kind of angle? Guys, let's go, come on.
A right angle?
Thank you, a right angle. We brought our eyes to school today, yeah?
Yes.
Okay, just
Took me
checking.
some time.
Okay, so we have a right angle. So the important thing to remember is that not only is it equidistant, so you have two congruent sides, but you also get a right angle. And that's going to be important. Okay, the converse of the interior angle, or angle bisector theorem. Can you read that as well?
If a point in the interior of an angle is equidistant from the sides of an angle, then it is on the bisector of the angle.
Right, so it's saying the same thing but backwards. So we always show the converse statements because the converse might not always be true for a statement that you make, but in this case, it goes both ways. So if the point is on the bisector, then it is equidistant. If the point is equidistant, then it's on the bisector. You can say it both ways. So I just wanted to include that. So take a second, write it down if you haven't. I should see pencils writing. And right now, I want to make sure that Daniel is writing things down, that Alejandro is writing things down, that Samaj is writing things down. I can't see you guys, so I don't know what's going on behind those screens. Great. Does anyone still need a second to write it down? Okay, great. So now let's use this theorem to help us solve some problems. So again, I'm gonna sort of summarize the theorem. The theorem says that any point on the bisector is equidistant from the sides. Okay. So can I have a volunteer read this problem? Tell us what it says.
It says that angle DAC is equal to angle BAD, and it's asking for the length of a side CD, and
Good.
you have to round 1 decimal place.
Okay, perfect. So I want to introduce you guys to this symbol right here. Let me explain what this is, because you guys will see it in the future. This is the first time we're seeing it. It looks like this. Looks like an O with like a line cutting through it. Does anyone know what that's called? I'm wondering. No? Okay.
Zero.
So it's not a zero. So it's actually a Greek letter. And the name of this Greek letter is called theta. So it's called theta. And we use it instead of we use it just in the same way as a variable, but usually we use it anytime that we don't know the measurement of an angle. So since we don't know the measurement of this angle, we call it theta. It's the same exact thing as a variable. So we use it just like a variable. But basically what this is telling us is that those two parts of the angle are equal to each other because they're both theta. Does that kind of make sense?
So it's like a fancier version of a variable.
Yeah, it's kind of like a fancier version of a variable. You guys actually, there's another Greek letter that we use in math. Does anyone know of a different Greek letter from math? You guys know, you've seen it before.
I can't remember.
I want to see if anyone can think of a Greek letter used in math that you guys have definitely seen before. You just might not know that it was a Greek letter. I'll
In
give you
algebra or geometry?
more so in algebra, but in general it's used. I'll give you guys a hint. Circles have it.
Um,
Hi.
Yeah, who said that?
Me.
Ooh. Yes, we've seen it before. Pi.
oh, I should have thought about it.
Pi.
Good job, Danny.
Pi is a Greek letter. Exactly. So you guys have seen that one before. But now we're using theta, and you'll definitely see theta again in other classes because this is used a lot in triangles, especially. Okay, so anyways, this is the information I have. And I'm trying to figure out the length of CD. Can anyone think of any relationships that we know of yet?
EB is 2.8.
We know that DB is 2.8, but is that going to be equal?
No.
Mm-mm. Anything else?
That point A is equidistant from both sides.
Point A, okay, so think about what you just said and maybe think it's almost right.
Uh, wait.
What exactly is equal? What do we know is equal?
AC and AB?
AC and AB, the line segments?
Yeah.
Are they though? Look, this is 5.9 and this one's 8.1.
You wanna say something? I was gonna say something.
Miss,
Yes,
how about like the both angles at the top? Oh wait, never mind. We don't know what they are. Never mind.
We don't know what they are, yeah.
Oh, can I take another guess?
Sure.
CD and DB
Say that again, CD
and DB.
and DB. You want them to be right? But
Well, we don't know that. Never mind.
yeah, we don't know anything about that.
Look at two
AB.
angles.
Oh, okay, wait, hold on. What did who said that? Jalen, can you say that one more time?
The angles?
The angles are the same. Yeah, we know that because they labeled it that both of them are theta. So I know that, and they also say it, DAC is equal to BAD. So all we know is that the angles are the same. So what does that make this line segment here?
A midpoint? Or
Close.
what's the name?
What's the other?
Bisector.
Right, this is a angle bisector.
Good job, Jalen.
Good job.
Thank
So
you.
what we can actually do, because this is an angle bisector, we can set up a little equation, and I'll show you exactly what it is. This bisector, what it did is it created two triangles, right? I kind of have like a triangle on top and a triangle underneath. And what we can do, I'm going to highlight these sides, is I'm going to set up a little proportion, because it turns out that, let me set this up. Okay. It turns out that AB, and let me just write down the letters and then I'll see if you guys can figure out the pattern. So AB over DB is going to be equal to AC over CD. So take a look at what I just wrote down. What is that telling me?
AB and AC.
The yellow one is trans something. What is that?
Called transitive.
Trans something. Yeah, that.
Transversal, but remember that transversals is when we're talking about angles, not side measurements. But here I'm talking about line segments. So what are they matching up? Take a look carefully. What are they matching up?
Angle B. No, wait. I'm gonna
Angle
stop talking.
A. Wait. Like something that's similar.
Yeah, so take a look, like what's in the
They both
numerator?
have A and D.
Which side length is in the numerator and which side length is in the denominator?
The numerator is
Wait, isn't that like 8.1 over 2.8, something like that?
Yeah, so this would be 8.1 over 2.8. And on the other side I have
5.9 over X.
yeah, 5.9. And since we don't know this measurement, we can call it X. But my question was, why did I match up 8.1 and 5.9 versus 2.8 with the X? Why did I put those two numbers in the numerator and the other two in the denominator?
Because of the symbol,
Which symbol?
the theta symbol.
Okay, but you're going too far into it. What's similar about AB and AC? What's similar about DB and CD?
Can you say that one more time?
Why did I put these two on top and these two on bottom?
Because they like match. The ones on the top both have A and the ones on the bottom both have D.
Not just about the letters, but look at them physically. Where are those located?
Oh, I know, like, but I don't know how to say it.
Say it however you want to say it.
Like
know.
AB and AC are like on the top, and like CD and DB are like on the other side of the triangle.
Exactly. That's exactly it, okay? It's based on where they're located. So AB and AC, they're the ones there, they are the, if this was an angle, which it is, remember what's happening. The angle bisector is cutting this in half, right? Okay. So the top, the numerator, that's the angle sides. Those make up the actual angle. And then the ones on the bottom, that's kind of like on the opposite end, right? Those are kind of like on the other side. They're across from the angle. So when you set up your equation, that's how it's always going to be. On the numerator is going to be the sides of the angle, and then the denominator is whatever side is on the opposite side. It's like cutting, it's like across from it. Okay, so now I have these numbers. Now I got to solve for x. If I want to get x by
Are we
itself,
dividing?
yes.
Oh,
But more specifically, what I can do, since I have two proportions, I have two ratios, two fractions, I can cross multiply. So I'm going to cross multiply. So here, what ends up happening is the 8.1 goes with the x. So this is going to be 8.1x. And then on the right side, I've got to multiply 2.8 times 5.9. What do I get?
16.52.
16.52?
Yeah.
All right. And now I divide both sides by
8.1.
by 8.1. So what's 16.52 divided by 8.1?
I got 2.52.
16.52 divided by 8.1. Not 2.52. You're close though. Does anyone else want to give me an answer?
2.03950617.
There you go. Okay, it goes on for a little while, but if I need to round it to one decimal place, what should my final answer be?
2.4.
2.4?
Wait, no, 2.04.
But that's two decimal places.
Wait, what?
Wait.
Just 2?
Just two. Well, 2.0.
Oh, because you have to round it to only one decimal point.
Mm-hmm. And the 3 isn't enough to bring me up. So this is just 2.0. Let's do another one. Let's see. I know that I need to make my little equation, right? So in this case, what goes on top, what goes on the bottom?
You do 5.9 over 2 and 8.1 over n.
Good. So that would be AB over BD equals AC over CD. So like I'm turning it, flipping it, Tyrone, but I'm doing the same thing. So I have 8.1 over X and 5.9 over 2. Now what do?
Cross multiply.
Cross multiply. What is 2 times 8.1?
16.2.
16.2, and then I have 5.9x. So on both sides, I just have 2.
Divide by 5.9.
Divide by 5.9. What do you get?
2.7456, etc.
Okay. And since I have to round this to one decimal place,
2.
one decimal place,
2.7.
2.7. Yeah,
2.7.
that's it. So this is what the homework is like, guys. It's not hard. You just have to have the right numbers in the numerator and the denominator. And that homework assignment, I'm actually going to give you guys an extension. It's going to be due on Friday. So I'll remind you at
Are
the
you
end of
talking
class.
about the homework on Khan Academy?
Mm-hmm.
Oh, I got an email on that. Sent it through today.
Yeah, I'm going to extend it and make it due on Friday. Okay, but I wanted to go over that because I put it up on Monday by accident. I didn't mean to put it up on Monday. So if you guys were like really confused about what it was, now you know, okay? You're gonna follow the same exact process that we did here and here. If you go home and do it and you kind of forgot what we did in class, you can always go back and watch this video. It's currently recording, so you'll be able to watch it and refresh your memory.
Miss,
Yes.
so the circumcised one is due tomorrow and the Khan Academy is due Friday?
Yes, and then there will be one more thing. I'll explain exactly what's due when, okay?
Okay, thank you.
You're welcome. All right, so now let's get to the actual main topic of today. Like I said, we're going to be looking at inscribed circles. So I have a few definitions. I actually have like 4 definitions here, just like we did last time. So can I get a volunteer to start us off with the first sentence? Okay, Tyrone, you can go.
I go
A
after
circle
Tyrone.
is
Yes.
a circle is inscribed in a polygon if each side of the polygon is tangent to the circle.
Good.
The
Jalen.
okay. In the figure, circle C is inscribed in quadrilateral WXYZ, and this circle is called the inscribed circle of the quadrilateral. I can't read for nothing.
You're good. You're good. Okay. And then here, okay, in order to construct this in circle of a triangle, you need to find the center of the circle. And this point is called the incenter of the triangle. Okay.
So it was like kind of like the circumcenter.
Yeah, it's there. Everything that when we did circumcenter, it was the word circum. Now it's the in. So circumcenter versus incenter, circumcircle versus incircle,
Oh, I get
circumscribed,
it.
inscribed. And it's pretty easy to remember. In means it's on the inside, circum means it's on the outside. So we'll compare that. Well, actually, let's compare that right now. So what I want you guys, while I'm drawing this out, just write down these 3 definitions.
Yes, I have a question.
Yes,
What does tangent mean?
I'll explain that in a second. Good question.
Tangerine.
Okay. That's pretty good. All right, so I've drawn here these 2 little diagrams. Let's go ahead and talk about them and label them now that we know everything we need to know. So on the left, I have what type of situation?
Inscribed.
Yeah, on
Right.
the left,
Impossible. Wait, in or M?
in.
In. I-N.
Impossible.
Oh, wow. And on the right, you have a circumcised. Circumscribed.
Yeah. Circumscribed. Circle.
Impossible.
Tongue twister.
Okay, now on the left, what is the center called?
Encircle.
The center, though, the point.
In center.
In center. And the actual circle?
Inscribed.
Nope. Look back at the definitions. What's the actual circle called?
Circle C.
Nope.
In circle.
In circle, yeah.
Oh, I mixed them up.
So the circle's
So
the
it has
in
to be
circle.
you.
The in center is the actual point in the middle. Now over on my other triangle, what's the center called?
Circumcenter.
Mm-hmm.
And the outside is the circumcircle.
Exactly.
Okay, I got it.
Circumcenter and circumcircle. So those are the differences. They're very similar, but one is on the inside, one is on the outside. So if that helps you, that is a really good little diagram to write down for yourself. And I'll give you guys a couple minutes to do that. Hi, Perla. All right, anybody still need a second to make these diagrams?
No.
Okay, so let's actually do this, guys. Let's go ahead and make our in circles. So if you're at home, go ahead and get your protractor, compass.
My there's something wrong with my protractor. You know how like the thing on that makes them like stay together?
Mm-hmm.
I forgot. Every time I move it around, it like moves like a lot. It's very loose.
It's very loose. Okay. Sometimes you can tighten it. Let me see. No, mine doesn't tighten, but sometimes you can actually tighten that part. If it's being very, very loose, what I suggest, sometimes you can get a rubber band and just tie the rubber band up at the top, and then that'll hold it together. But if it's
Sounds
being,
smart.
yeah, if it's being kind of challenging, then try your best with it. See if maybe you can get another one, but I'm not telling you that you have to get another one because I understand things get broken sometimes.
I had a hard time doing that. The circle homework.
Because of that?
Yes.
Okay, try the rubber band trick. If that doesn't work, you get an excuse, but I'll give you an extension. So until you can figure out, maybe get another one or do something to fix it, okay? All right, so let me just set up. Who is calling me? Okay. All right, we're good?
Yes.
All right, does anyone still need a minute to get their supplies out? Daniel, you got everything you need? Alejandro, you guys got everything?
Perla got kicked out again.
Oh, okay.
Yeah, her computer went black.
Okay, well, follow along from the Promethean. Luckily, this part doesn't involve a whole lot of talking or anything. Okay, so I'm going to be making my in circle. I'm just trying to get my headphones out of the way. Hold on, guys.
I have a rubber band, but where do I put the rubber band on it?
You could try tying it around the top part over here, just so that it keeps it tight. But you don't want to make it so tight that it closes it shut. So I guess, try and see if there's a way to make it tight enough that it won't open, but not so tight that it closes on itself.
Okay.
All right, so inscribed. Circle of a triangle. And again, it's on the inside, so we want our final thing to look something like this. Okay? So step 1, we are going to make a triangle. And if you have a whole sheet of paper like I do, it's good to make it really, really big because then you have a lot more room. I know some of you guys, when you sent me your pictures for the circumscribed circle, you made it kind of small. For this one, I would definitely make the triangle pretty big because it'll give you more room to make the circle on the inside. So the bigger your triangle is, the better it's going to turn out. So step 1, make a triangle. And I'm going to label mine A, B, C. And once you've got your triangle, what you're going to do next is to make the angle bisector of angle A. So here's angle A. I want to draw my angle bisector. So what is that going to look? What is that going to do? That angle
It's
bisector.
gonna cut it in half.
Right. I'm going to make a line that goes all the way across, and it's going to cut that angle in half. So here's how we do that. To make an angle bisector, you take your compass, you set it to any width, basically. You don't want to go too wide either.
Or else it'll be hard to hold.
Yeah. And you're going to put it into the point A and just draw an arc that goes across, just across the whole angle. Okay. So I'm just making this arc. And I'm not gonna label it, but I'm just gonna put a little point down where it crosses each side of the triangle so that I know where to go next. So now that I've made this arc, I'm gonna go to each of those points. I'm not gonna change the width of my protractor. I'm gonna go to each of those points and make an arc right above. Then I go over to the other one and make an arc that crosses. Okay, so I didn't change the width at all this whole time, but I stuck it into that intersection point and made an arc above, went over to the other intersection point and made another arc that crossed. So now I've got this point of intersection right here, and what I'm going to do is I'm going to connect it to point A. So this point of intersection that I created gets connected with point A, and I'm going to make it pretty long. All right, so I made my arc, I didn't change the width, and I made 2 different arcs off of those points, and then I connected them. Questions so far?
No.
Awesome, and now notice that this whole angle A has been cut completely in half. Now I'm gonna do the same thing. Oops, make the angle bisector, but this time with angle C. So I'm gonna make an angle bisector again, but this time using angle C. So I'm gonna like flip this around just so I have it there in front of me. And I'll do the same thing. I'm not gonna make this too wide. I'm going to draw an arc. So I stick it into point C and I just draw one long arc. Oops. There we go. Okay, and then I go over to where it crossed over here and over here. I stick it into each of those points and draw another arc, and both of those arcs will intersect.
Hey, we do this for all angles.
We're only going to do it for angle A and C. We only need to do it for 2 of them because it automatically works out that way. You don't have to do it for all 3. I mean, you could, but it'll end up at the same place. All right, so I made one angle bisector. Now I'm making the other one. Same as before, I connect that intersection point with point C. And just go pretty far, but not too far, because now I see where they connect. So this point right here, that's my in-center. Okay, so I'm almost there because now I have my in-center, so I know where the center of the circle is, but I don't really know the radius of the circle. I don't know how long or how big that circle is going to be quite yet, so I can't draw the circle yet, but I'm almost there. Any questions so far?
No, I understand.
Cool. So here's step 4. Step 4, now that we have the in-center, we're going to make a perpendicular line from the in-center to AB. So basically what I want to do is I want to go from this in-center, I want to make a line that goes to AB and touches AB at a 90-degree angle. So I want there to be a line, and that line is going to create a right angle. So here's how we're going to do that. Is everybody caught up? Anyone need a second to catch up to me?
Yes.
Okay, I'll give you guys a second. Catch up. Let me know when I can move on.
Okay, I got it.
Okay, cool. So again, I'm going to make a right angle. I want to make a right angle from the in-center to AB. So I take my compass. I'm going to put it into the in-center and then just make it wide enough so that it touches AB at any point. You just want to make it a little bit wider. Doesn't matter how wide. And let me just align this a little bit better. So I stick it into my in-center, and I'm going to make an arc on one side of AB and then swivel it around, and on the other side. So I'm basically just making an arc over on one side and then over on the other side. Doesn't really matter how wide your compass is, as long as you make one on one side and then over on the other side. And then I'm not changing the width. I'm going to keep the width exactly the same. I stick my compass into one of those intersections and draw an arc. I stick my compass into the other intersection and draw an intersecting arc. Okay, so what did I do? Again, I set it at whatever width I wanted, as long as it crosses AB, and then I made an arc on one side and then over on the other. So I kind of went over here and then I swiveled it around and went over there. And then without changing the width, I stuck it into one of those intersections and made an arc, flipped it around, stuck it into the other intersection and made an arc. And so now I'm going to connect my in-center with that intersection point. And what that does is it makes a perfect right angle. Okay. We're almost there. So as you guys finish
Make
that
a
step,
circle.
yeah, so now we're gonna set the compass to the width from the in-center to, let's call this point, let's call it point M. To point M. So now I'm taking my compass and I'm going to make sure it's the same width from the in-center to point M. Okay, so now it is at that correct width, and then from
Then
there
you draw.
I can make my circle,
Yay.
my in circle. So let me move things around. Okay, ready? Let's hope it worked, guys. It didn't work last time, if you remember. Let's see if it works this time. Oh, hold on. My compass widened a little bit.
Uh-oh.
Uh-oh. There we go. Okay, let me try again. No, why is it still wide? It's too wide. There we go. Okay. It's kind of hard to turn the paper. Okay. This one's really hard to get perfect. So mine's not perfect, but it's pretty close.
Okay, Miss Lopez.
There we go. There is my in circle.
Wait, do you have to do the right angle part, or
You
you don't need
have
it?
to. You have to do the right angle part because this measurement from here to here is the radius of the circle. That's telling me how long or how big that circle is going to be. So if you don't do this step, your circle is not going to be the correct width.
Okay.
Okay. Do I have questions? So this one has some similarities and some differences to the circumcircle. Let me see if I have my circle. I do. Oh, I know this one was the bad one. Remember I did it once and it didn't work out? Okay, here it is. I had to rip a part of it, but here's my circumscribed circle. So let's look at the similarities and the differences. Look at circumscribed. We had to do the perpendicular bisector of AC. Then we did the perpendicular bisector of AB. What's the difference here? Here we had to make the angle bisector of angle A, and then the angle bisector of angle C. So there's some similarities. We have a bisector, but different types. This one's perpendicular bisector, and then this one was angle bisector. And then this one, we had to also make a perpendicular line right here, this right angle, before we could finish off. Whereas here, you were kind of done after step 2 and step 3. You just had to set the compass to the right width, and then that was it. You were pretty much done. You didn't have to do much more. So circumscribed is a little bit easier than inscribed, but okay, we got to know how to do both. So for homework, you're going to make an inscribed circle, and this one's going to be due on Thursday, tomorrow at midnight.
Wait, Miss,
Okay.
I need to take a screenshot real quick.
Okay. So inscribed circle by tomorrow at midnight. When is the circumscribed circle due?
Tomorrow.
Nope.
Wait. Today at midnight?
Today at midnight, yeah. So this one's due tonight at midnight. This other one's due tomorrow at midnight.
Okay, I got it.
And yeah, just send me a picture on Remind. If you prefer another way, you can get me on Instagram or my Google phone number.
Wait, can I see
Okay.
the other one, the circumscribed one real quick?
Mm-hmm.
Okay, thank you.
You're welcome. Okay. So that is the homework. And what time is it? We have a little bit more time to get through a couple more slides, but that's the main part of today's lesson, okay? So let's just get back to the notes. All right. So now we have an in-center theorem. Of course we have a theorem, right? Every time we learn something new in this class, boom, you got a theorem. So can I have a volunteer read the in-center theorem?
Me.
Go ahead.
The angle bisectors of a triangle intersect at a point that is equidistant from the sides of the triangle.
Perfect. So what we did just now when we made our in-center, okay, so this point right here, this is the in-center. Notice that what they're showing us here is very similar to what we actually just did physically. We made an angle bisector of A. So that was our first step. We did this. Then we made the angle bisector of C, which is that. They crossed at the in-center. And then what did we have to do after that?
Wait, what did you say?
I just realized that it's not loading for you guys, is it?
Oh, I can see it now.
It's like
Like
it's really lagged.
Like the line you drew about
Yeah.
P up is blocked.
Uh-oh, hold on. It's acting up.
Miss Lopez having technical difficulties 101.
Technical
Insert
difficulties.
Jeopardy theme.
There we go.
Oh, I see it now.
Now we're good. Yeah. So those were the two steps that we did just now. We made the angle bisector of A, the angle bisector of C, and then they connected in the middle. That was the in-center. And then what did we have to do that that Jalen asked me if we have to do it, and I said, yeah, you do have to do it.
You had to make the right angle.
Yeah, we had to make that right angle, right? So you can't skip that step because that's the whole definition. The definition of an in-center is that the angle bisectors of a triangle intersect at a point that is equidistant from the sides of the triangle. So all of these segments that I'm highlighting in purple are equidistant. Equidistant. So all of those are equal. Okay. So it's kind of similar to what we did on Monday. So let me take a moment through memory lane. This is what we did on Monday. Okay. So when you have the circumcenter, look very, very carefully. When you have the circumcenter, look at what is equal. Okay? In this case, whatever is equal is connected to the vertices. So those green lines, they go from the center to each vertex, from the circumcenter to point A, from the circumcenter to point B, and from the circumcenter to point C, right? Well, now which ones are going to be congruent? Not the ones that go out to the vertices, but instead it's these purple ones that create those right angles. So it's the bisectors, the perpendicular bisector. So it's very similar, but a little different. And we have to remember which one is which. Okay, so for in-center, when you're at the in-center, you have line segments that are congruent this way. That's the in-center. But when you have the circumcenter, you have line segments that are congruent in this way. They go out to the vertices. Do I have any questions about the differences between those two?
No.
Okay.
No.
So now let's go back. Oh wait, no, this is where I want to be here. Okay. So there's our in-center theorem. So that's going to allow us to do a couple of problems that we can solve. We don't have too many. Look, we only have 3 slides left, so we'll be done pretty soon. All right, so here I know that QX and RX are angle bisectors of PQR. Okay, so QX is an angle bisector, and RX is also an angle bisector. So the place where they meet, what is that called?
Carla said the circumcenter.
Close, but you're thinking of the wrong one. This
Wrong
is my
one, Carla.
circumcenter. Right, so this would be the circumcenter, so it's the other one. It's the
Center.
in-center. Okay. Okay,
Carla
so
being
then,
wrong 102.
so then it wants me to figure out the distance from X to PQ. Okay, so let me draw that out. Hold on. Let me relabel this. Okay, so from X to PQ, here's PQ. Okay, if I want to connect X with PQ, I have to make sure that it creates what type of angle?
A right angle.
A right angle. So that's what they want me to know. I want to know how long that segment is going to be. Well, what do we see on the diagram that can help me out?
Wait, can you repeat that?
What do I see on the diagram that might help me figure out the measurement of that red line segment that I'm looking for?
E? Wait. Oh wait, the red line segment, like next to X. Oh, that. You're like XY.
XY, yeah. XY is also making a right angle. So I know, since both of these make those right angles, what do I know about them?
They have to be the same.
They have to be the
They're
same.
congruent.
They're congruent. So the distance from X to PQ is also going to be,
Equidistant.
yeah, it's going to be 19.2 units. What about the measure of PQX? PQX. So let me erase what I have. Okay,
Wait,
PQX.
PQX?
PQX, yeah.
I
I wish I had made this a little bit bigger. Matter of fact, let me make this bigger. Give me 1 second, guys, because I don't have enough room to write.
Maybe XYR?
Hold on.
Oh, okay.
Nice, okay. So P, Q, R, and we've got this situation. Okay. It's pretty good. All right, so it's asking us for PQR, right? No, PQX, sorry. PQX. So angle PQX. It wants us to know how much that measures right here. Well, let me fill in a couple of things. I know that this is 52. right? Degrees.
Y is 19.2.
Y is 19.2. Mm-hmm.
And R is 12 degrees.
Mm-hmm. And we also, in the previous problem, made this line segment here, which created a right angle, right?
Yes.
So this was a right angle, and it was also 19.2. So that's all the information I have so far. Is it possible to fill in anything else?
Maybe,
Maybe.
Oh, I also know, so hold on. Let me erase some stuff to make this clear. I also know one more thing, which is in the problem, or in the diagram they give me, which is that this part right here, this tiny little sliver, is 12 degrees, right? So let's think about this. If that's 12 degrees, what about the little sliver on top of it?
also 12 degrees.
Yeah, why?
Wait. Is it because of the bisector?
Yeah, because what does it tell me about Rx?
They're bisectors of PQR.
Right. So I know that this line segment here is a bisector. So it's cutting it in half. Therefore, both sides have to be 12. Okay? I know that for sure. So that means what's the whole thing, that whole angle,
Wait, where?
before it was cut in half by the bisector? If each part of it is 12, what's the whole thing? Angle R.
Is that 24?
Yeah, 24, because the whole thing has to be 24.
Oh yeah,
So
before it was cut in half.
yeah, so now let me simplify everything. Let me label only what I know. So I know this is 24. I know the other one is 52. And I know, what do I know about QX?
The base of circumscribed circle of the triangle.
QX.
He said inscribed or circumscribed? Ascribed.
Is it inscribed or circumscribed? It's inscribed. We already knew that from before, but that's not what I'm asking. I'm asking you, what do I know about QX?
QX is a bisector.
Is a bisector of angle what?
Wait. PQR.
PQR. Yeah, PQR.
PQR. So if I know, so far, let's summarize. I know this one is 52. I know this one is 24. What can I find?
Q.
Yeah, I can find Q. How do I find Q?
Wouldn't Q be, wouldn't this triangle like equal 180, so we would have to add them up?
Exactly. So I know that 52 plus 24 plus Q, which we don't know yet, has to equal 180. So what does Q have to equal?
104.
104. How'd you get that?
I added 52 plus 24, and then I subtracted it from 180.
Good. So if the whole thing is 104, oops, sorry.
And 52 plus 24 is 76.
If all of angle Q, this whole thing, is 104, but I'm only asking for PQX. So what is PQX?
Oh, it
then?
divides it in half.
Divided in half. So what's 104 divided by 2?
52.
52. So if that whole thing is 104, then PQX, since I know that that's an angle bisector, it's going to be 52. Whew, we got there in the end. So, you know, a lot of these problems, they require you to think back like a long way. Because remember, this whole thing where it has to equal 180, we learned that a long time ago, right? But it always comes back. All of these things build onto each other. And that's how we're able to solve these kind of challenging problems. Okay, let's just summarize everything we've learned. Can I have a volunteer read? What is this? P is what?
The in-center of ABC. Determine triangle ABC.
Mm-hmm.
Determine whether each statement is true or false. Select the correct answer for each lettered part.
Okay, let's go through it. If this is the in-center, true or false, point P must lie on the perpendicular bisector of BC.
Yes. True.
So what is BC? What's the perpendicular bisector again?
Perpendicular bisector is
What's a perpendicular bisector?
it cuts it would cut triangle ABC in half.
Okay, not triangle ABC, but here it's saying the bisector of
Side BC.
side BC. So it'd cut this in half
And it would create a 90-degree angle.
and create a 90-degree angle. Very good. Does that work out?
Yes.
That crosses point P?
Oh wait, no.
No, I'm just eyeballing it here, but yeah, I'm pretty sure that's not going to cross through point P. And the reason for that is, remember, go back to what we did. Remember that when we made the in-center, in order to figure out this point, when you actually construct it, what was step 1 and what was step 2?
Draw a triangle.
Okay, after that though.
Oh wait, I took a picture. Then you would have to make a perpendicular bisector.
Nope, read again.
Wait, I have to zoom. You have to make a angle bisector of angle C.
Angle bisector, not perpendicular bisector.
Angle.
Angle bisector.
Also, it's false.
So it's false because remember that perpendicular bisector would not make the in-center. What would that make?
The circumcenter.
Circumcenter, exactly. So this only works if you're trying to look for the circumcenter. All right, B. Point P must lie on the angle bisector of angle C.
Yes.
Yeah, that's true. Angle bisector. C. If AP, so AP is 23 millimeters long, then CP must also be 23 millimeters long. True or false?
False.
False. Good. This is false because remember, when you have an in-center, these three are not going to be congruent. That's for circumcenter. So that's why we got to think of the differences, okay? So that's not true. D, if the distance from point P to AB, so this 90-degree, hold on, let me do a better job. So this 90-degree guy, if the distance from point P to AB is x, so if this is x, then the distance from P to BC, this one right here, must be x. True or
True.
false? Good, this is what's true. Since this is an in-center, then I know that these three segments would be equal. All right, and then finally, the perpendicular segment from point P to AC, okay, so that's talking about this segment, is longer than the perpendicular segment from P to BC. Is that true or false?
It's false because we already discovered that they're all the same
Yeah,
length.
we discovered that all three of these would be congruent.
False, true, false, true, false.
All right. So that was kind of summarizing everything. I hope that that clears up the difference between in-circle and circumcircle.
Yay, no proof. Oh no,
You thought
I spoke too
you
soon.
spoke way too soon. Let's go
Given
through this proof. All right. Given PS bisects QPR. So let me just color code. So this is my bisector. My what type of bisector again?
Angle bisector.
Angle bisector. That's given. Okay. And then it also gives us that SQ is perpendicular to PQ and SR is perpendicular to PR, which we also know because it gives us what type of angle?
Right.
Right. We also know this because of the right angles. Okay. Then QPS is congruent to RPS. Look at the angles that they're telling you about. QPS is congruent to RPS. How do I know that?
Aren't they like corresponding or something?
No, I mean, no, they're not.
In center. Wait.
What in-center? There is no in-center here. So
Because,
QPS is congruent to SRP or RPS. How do I know that? How do I know?
Well, Q and R are both right angles, so they would be congruent.
But that doesn't tell me anything about QPS and SPR. How do I know that QPS is congruent to SPR?
Wait, isn't it like because PS cuts it in half and it cuts it into equal parts?
Exactly. So what can I use?
The angle bisector theorem?
Not just the angle bisector theorem, but the You're right. You know that it's because of it's an angle bisector. So what do I write when I know that it's because it's an angle bisector?
The definition?
Definition. Just gonna write def of angle bisector. Okay. Then they tell me that SQP and SRP are right angles, and that's because that's the definition of perpendicular. Then they tell me that SQP is congruent to SRP because all right angles are congruent. Okay, where can I use the reflexive property?
PS is congruent to SP.
Good job. PS is congruent to itself. So I know that this is congruent. And I also know from the previous, which I didn't label yet, that Q and R are congruent.
All right. Yes.
They're right angles and they're congruent to each other. So what statement can I now make about the triangles that I have?
AAS. Wait. No,
AAS is the reason, but what's the statement?
QSR is congruent to RSQ.
PRS.
Good job. Yeah. Now I know because I have AAS, I know that triangle. Let's see. I'll do QPS is congruent to triangle RPS. Good. Okay. And since I know that these triangles are congruent, now I can say that SQ is congruent to
CTCPT. CTCP.
CP.
CPCTC.
There you go. CPCTC. Exactly. Because again, CPCTC only works. You prove the triangles are congruent. Now you can pick out a part from the triangle and call it congruent. And now that concludes, that's everything. And now I know that
easy proof.
SQ equals SR because congruent segments have the same length. So
Paula would have loved this.
There you go. Easy proof.
Yes.
All right, and that is all for today, guys. So like I said, I'm giving you an extension. Homework will be due, so the Khan Academy homework is due on Friday. The Khan Academy homework is due on Friday, but what about the two constructions?
The circumscribed one is due today at midnight, and the inscribed one is due tomorrow at midnight.
Good. Circumscribed is due today at midnight. And then the inscribed is due tomorrow at midnight.
Question.
Which
time are we following? Because on my computer it says, wait, hold up. It says 3:16, but on my phone it says 2:16. Which one am I following?
The one that is true, which is that it's 2:16.
Okay, because I kind of went to school in like 8, like literally 8 in the morning.
Oops.
Oh no.
Oops. Well, you'll have to see if you can fix it on your laptop so that it matches.